This conference will now be recorded.
So welcome everybody. Really happy and excited to have Amir Agakuchak from the University of California in Irvine to talk to us about some of his work on the cascading and compound disasters. Amir is a professor at UC Irvine. He heads up the Center for Hydrometeorology and Remote Sensing, CHRS. Amir and Lisa, and specifically the active climate cluster, we go back a few years. 2015 at the ESUP summer meeting in Asilomar, California, Amir was an invited speaker at one of our sessions. And then subsequent to that meeting, two of his former students were also invited speakers at the time we were doing these workshops, climate resilience toolkit workshops, CRT workshops, to generate case studies for the CRT database. So we've had quite a bit of interaction in the past, and I'm really happy to have him come talk to us about his work on compound cascading disasters. And if you were at the first November meeting that we had, you remember that Batu Asmanulu of the Goddard Disasters Program, he's one of the coordinators. So he gave the kind of the Goddard perspective on cascading disasters. And then the second half of November, Thomas Harris and his couple of his colleagues from Planet talked about their work in disaster monitoring and response, including wildfires. So really looking forward to hearing what Amir has to inform us about his work regarding cascading and compound disasters. Amir, I'll hand that off to you to start. Thanks.
Thanks for the introduction, Bill. I'm happy to be here with you today. Instead of going into one single paper in detail, I will talk about a series of publications related to this topic of compound hazards, different topics, coastal floods, droughts and heat waves, and also snow-fire interactions. Let me quickly explain what I mean by compound event. Let's consider a coastal system. You can get flooded by the ocean alone, or you can get flooded by rivers. We call it fluvial flooding or terrestrial flooding. And also direct rainfall can contribute to flooding. We call that pluvial flooding. So there are at least 3 different drivers that can interact with each other. When there's a hurricane or a tropical storm, we have extreme rain inland and also surge. And rain inland drains toward the ocean, and this large-scale event creates compound event with drivers that are physically and often statistically related. But we don't necessarily need a hurricane. Even in Western US, atmospheric rivers create more or less the same situation, less intense, but still much smaller scale. Also, randomly, you can have rainfall at the same time as high tide, king tide, spring tide, and those sort of above average high ocean water levels. And we know the amount of water that can drain from river to the ocean is a function of the gradient, and the lower the gradient, or the higher the ocean water level, less water can drain into the water. And in extreme situation, river can even go backwards. And that contributes to backwater and increased flood impact. So how do we handle this in our guidelines? Currently, we treat them separately. If you look at USGS guideline for flood frequency analysis, we ignore the ocean water level dynamics. We don't consider that dynamics in the way we calculate our 100-year flood. If you look at NOAA guidelines for ocean water analysis, again, we ignore the dynamics of the terrestrial flow. FEMA has a guideline for interactions between different drivers, but even that guideline in a paper 2019, we showed that even that one underestimates the interactions between different drivers. So there are different types of compound events. You can have two extreme events happening at the same time, or two non-extreme events, but if they happen at the same time, they can amplify each other. For example, a moderate drought and above average temperatures, if they happen together, it is individually, they may not be extreme, but if they happen together, for example, they can lead to extreme impacts on crop yield. So some kind of extreme impact, but with non-extreme drivers. But in this case, drivers that can interact with each other. You can even have events that happen in a cascading form, like rain over burned areas causing debris flow, or rainfall triggered landslides. Those are also forms of compound events. We have a more general definition in this 2018 paper, in which we linked compound hazard definition to this definition of risk, hazard, vulnerability, and exposure from IPCC. So we have compound events with climatic drivers like droughts and heat waves, runoff and surge, but we have also compound events with non-climatic drivers, mainly human activities. For example, if urban expansion increases your flood risk over time, you can argue that this is also a kind of compound event, but with a non-climatic driver, in this case, urbanization. The same applies to deforestation and so forth. Before I start, most of the methods I present are already available on my website in these two different software packages. One of them is called MVCAT. It is designed to analyze different hazards and their relationship with each other. So this includes the source code and also a graphical user interface for those who don't want to deal with coding. It allows you to, it's written in a general form, so it's not for a specific application. There are 27 different multivariate models built in there. It allows you to look into your drivers and see if they are related and how they are related. And the second one, MAST, for multi-hazard scenario analysis toolbox, allows you to create bivariate or multivariate return period, return level curves. So for example, estimating your 100-year flood, but considering multiple drivers. And both include a graphical user interface, and also a paper comes with each that explains the details. So I don't go into the details. The second one also includes different so-called hazard scenarios. And those hazard scenarios define how hazards interact with each other. If you're looking at two hazards happening exactly at the same time, or you have two hazards, but one alone can cause significant damages, so you go with either or both at the same time. So again, mathematical details are available in this GRL paper, but let me go into specific examples. First, compound coastal flooding. We looked at 8 major basins, coastal basins in the US, where we had 80+ years of data, and we could look into the interactions between ocean water level and terrestrial flows. And when you want to analyze compound events, you need to have a so-called hazard scenario. I briefly mentioned, for example, the one on the right. You can see, let's say ocean water level is the y-axis, discharge, river discharge is the x-axis. You need to have 2 thresholds, one for river discharge, above which you get flooded, and another one for ocean water level, above which, again, you get flooded. Ocean water level thresholds are available from NOAA. So you have these 2 green lines, and anything above is considered hazardous. And if you have an or hazard scenario, you end up with this shaded area, and you extract values above, and you use this for your compound coastal flood analysis. There is another concept called Kendall, the one on there are different left, which gives you a front, and you look at everything above. So there are hazard scenarios, but there is cause devastation. Available in this paper, 2017 PNAS paper. But the way we look into impact, we translate everything into the so-called reliability theory and failure probability. If, let's say, you have a levee or a seawall, and it is designed for, let's say, 50 years, we use a simple reliability theory equation called failure probability that gives you what is the failure probability over the lifetime of whatever you're looking at. Could be a levee or a seawall or anything else. Or in general, inundation above a certain level. And here T is design lifetime in this equation, and P is probability of the event that you're considering, like a 100-year event, 200-year event. And this method gives you something like this green line here, where you have probability of failure over time. We extended this commonly used equation using multivariate methods to the one below. It's called multivariate failure probability, where instead of one probability, you have multiple probabilities, multiple hazards. And C in this equation is a multivariate model that links different hazards. Again, the details are available in this paper. So here is an example. This is Washington, D.C. area. And the black line is the commonly used failure probability with one hazard at a time. In this case, if we consider both fluvial flow and ocean water level together, then we end up with the red line. As you can see, red line is above the black line. This means that by ignoring compounding effects of different drivers, we underestimate risk of failure. And in this paper, we also looked at sea level rise scenarios. So that's the purple line, and the dotted lines are the uncertainty bounds. So this model allows us to replace our historical ocean water levels with future sea levels and recalculate our failure probability. By the way, failure probability here means hydrologic failure. If you have a seawall designed for, let's say, 100-year ocean water level, if a 100-year ocean water level happens, theoretically, this failure probability will be 1, but physically, it may not fail. We have another model that translates failure probability into physical failure probability. That's a finite element numerical model. It's a whole different story. I'm not talking about that today. We looked at different areas around the US. We see more or less the same pattern. Again, under sea level rise situation, you quickly get to probability of 1. It means some of the infrastructure will reach design thresholds, but again, that doesn't necessarily mean physical failure. For physical failure, we use a different model that again translates hydrologic failure probability to physical failure probability. Just to give you an example of a flood extent, so here we have also a 2D model that translates different coastal flooding scenarios under compound event and translates into flooded area. So you get what areas will go underwater. So there is a paper on this topic in Advances in Water Resources. This method allows you, again, currently we are ignoring how different interactions will change area that goes underwater. This is based on a numerical model, and we use this to basically see how infrastructure will be impacted, like seawalls, levees, and so forth. By the way, the code to generate hazard scenarios, the one on the left, is available on my website, and the code to generate to calculate flooded area for a 1D version is also available. It's the one on the right. So if you want to test it in your own area, you can simply do this on your own. So why this is important? In some areas, like here, you're looking at 2 different locations. The one on the left is location in Alaska, where we have a beautiful estuary that will likely go underwater in the next 50 years. It will this area that you're looking at will probably disappear completely, but there is no physical boundary upstream, so another estuary will evolve later, maybe a different ecosystem, but there will be another estuary and capacity for flood control upstream. But the one on the right is an area close to where I live. We have, again, a beautiful estuary that will, at least part of it will go underwater in the next 50 years. But there is a physical boundary here. There is an urban environment that limits this estuary. There is no room for further evolution of estuaries upstream. This means that under future sea levels, part of this estuary will disappear, and part of, basically, some of your capacity to hold floodwater will disappear. This means that flood risk will significantly change in an area like the one on the right, where you have physical boundaries in coastal systems. One of the issues we have when you look at coastal floods is lack of really spatial data. We do have river gauges, but when it comes to flood extent, we have limited information. We have some satellite imagery, but they are infrequent. But hopefully the upcoming SWAT mission will give us a better understanding of inundation in coastal areas, and hopefully with this mission will improve our understanding of interactions between different drivers. Another example, droughts and heat waves. If we look at data in the southwestern US, we see that temperatures have increased by around 0.7 Celsius, a little less than that. But if you look at temperature change during drought events, the rate of temp change is twice higher, is close to 1.4 Celsius. This means that droughts are warming much faster than the average climate. We know why. There are a bunch of papers on interactions, that land-atmosphere interactions that exacerbate drought and heat wave co-occurrence. We also looked at this issue in this Science Advances paper, looking at different drivers, including vapor pressure deficit, relative humidity, soil moisture, and so forth. So we know why this is happening, and this pattern is more or less happening in the entire southern US and also Midwest and Northeast. A good example are relatively recent 5-year drought in California, where we had record high temperatures multiple years in a row and record low precipitation. And if we look at these two drivers individually, we see that, for example, empirically, rainfall was around 24-year event, which is extreme, but not that extreme. But in 2014, in terms of impact, the drought was really, really extreme because temperature was very, very high. And if you look at temperature alone, it gives you a 120-year event based on current data and in an empirical way. But with the method I mentioned earlier, if you look at them together, look at the co-occurrence, then it gives you kind of like a 200-year event. So this means that if we look at drivers individually, we underestimate the risk of this particular event because it has two significant drivers that interact with each other. The details is available in a GRL paper, 2014 GRL paper. Again, I don't go into the details, but you can find it on my website. Now, a little bit about snow, temperature, fire interactions. We know in many areas, like in Western US, temperature and snow are obviously related. With warming temperatures, snow can melt faster and cause flooding in spring, but also dry conditions later in summer, especially late summer. So snow temperature interactions have both consequences for floods and droughts. And not only that, they can also cause this sort of cycle of flood and drought in a relatively short period of time, especially if temperature rises really quickly, you end up with rapid melt, flooding, and then shortly after you're in drought condition. Even in California with all the reservoirs, there is no way that this rapid flooding can be captured. So most of it should eventually drain into the ocean. And then basically you end up with low water conditions in summer. So this not only has direct impacts, but also some cascading consequences that we are investigating now. Using again the methods I mentioned earlier with some modifications, we looked into SWE, snow water equivalent, from satellite data and also model simulations, basically composite products, and temperature to understand the interactions between these two. So the PDFs you're looking at, the top figure, are PDF of snow water equivalent for different temperature levels from around -1 degree below long-term average to around 1 degree above. As you can see, the higher the temperature, the peak of SWE shifts to the left. It means lower mean snow water equivalent, and that shift, I'm sorry, that shift means a rapid melt and less SWE availability later in spring and of course summer. So this method allows us to put every 1 degree into perspective. So this method is available in this 2018 PNAS paper, shows that for every 1 degree change, we end up with 20% change in snow water equivalent availability at a fixed time, like April 1st. That means the peak shifts earlier and drains earlier, and higher chance of flooding in early spring. And in a follow-up paper in 2020, we also provide a snow drought data product based on, not based on this method, but based on some of the data and methods we used in this study. So that's also available online. It's a global data set. Now, we know these two drivers, temperature and snow, are related, and they interact with each other, and they have flood and drought consequences. Now we have another player in between that is kind of becoming more and more important, and that's wildfires. Wildfires are not only increasing in terms of size and severity, they are happening at higher and higher elevations. So the figure on the bottom left shows you wildfire elevation in thousands of meters. So 3 means above 3,000 meters. And this is really interesting because this is from Sierra Nevada, and we see that the fires are happening above snow line, and actually very frequently and in large sizes. So when snow later falls in a burned area where there is no canopy, the radiative forcing then is completely different. So snow is more exposed to radiation. It can melt even faster and cause even more devastating flooding and more severe droughts later. So these wildfires, it's hard to quantify the effect of wildfires, but we are working on it right now. We have a fieldwork project where we are collecting data from burned and unburned areas, including soil moisture and infrared data with drones and hyperspectral imagery. And the goal is to basically quantify change in radiative forcing. That's work in progress. But we know we have already seen these fires at high elevations, and to what extent they intensify compound and cascading hazards related to this snow fire temperature interaction is still kind of unknown. It's definitely there, but and it needs a lot of work. Now, when you look at fires alone, I don't go into details of this paper. We have one recently published that looks into the effects of change in precipitation and temperature on severity of wildfires. Based on, again, the models I mentioned earlier, the toolboxes I mentioned earlier. So we can look into the same way we looked at temperature and snow, we can do the same thing for temperature wildfires, snow wildfires. The question is how to bring all of them together. And that's what we are doing right now. It's work in progress. But there are some types of compound and cascading hazards that are very difficult to quantify their risk. One of them is rain over burned area. We know that if you have extreme rain over a burned area, there's high chance of debris flow and flooding. This figure, the one on the left, is a hillside near Santa Barbara. This is exactly where rain over burned area caused massive debris flow in January 2018 that killed 23 people, I think. And this is exactly where it started. But the photo is taken like 2 years, 2.5 years after the event, 2 years after the event, almost 2 years. So you can see the vegetation has recovered a little bit already. When it comes to rain over burned area, the issue is we have drivers that can happen like 6 months or even a year apart from each other. And if you investigate them from statistical viewpoint, they can be completely independent from each other, but we know that they are related through their impact. And impact in this case is debris flow. So the question is how to look at compound hazards or cascading hazards. Cascading is a kind of compound event that with independent drivers. All the other examples I mentioned, we know that the drivers are related, and that relationship is not only can be explained physically, but also statistically. That's why the methods we have developed and made available online can be used for all those events and similar events. But in this case, the same models I mentioned earlier, they won't work if you're looking at rain over burned areas. So for these models, so this method I mentioned earlier is not going to work for rain over burned area. So what we are doing, we do everything backwards. So we try to find the impact and then investigate the drivers from a physical viewpoint and see how we can build a relationship in a kind of completely backward framework, which is not easy. This is work in progress. One of my PhD students is working on it. This requires looking at not only a lot of satellite data, but also physically based models to link different processes. So we look at satellite wildfire data, satellite soil moisture data, and also a lot of in situ measurements of sediment, downstream sediment, and rainfall. So this is work in progress. I don't have reports on this, but hopefully soon. Again, these toolboxes are available on my website. If you have any questions about them, I'll be happy to answer. So if I want to summarize quickly, if we ignore the compounding effects of different drivers, we underestimate the risk of almost everything, whether it's coastal flooding or drought and heat waves, it doesn't matter. Unfortunately, in our current guidelines, especially guidelines that are used by consultants, we systematically ignore these interactions between different drivers. The same applies to drought and heat waves and the way we do risk assessment. We have some models out there that can be useful, but still those models cannot help us with compound events with kind of independent drivers. This is my research group. These are the guys who do the hard work. I'll be happy to take any questions you may have. Thank you.
Thanks, Amir. Wow, that was really interesting stuff. You guys are your group is doing a lot of interesting work. Before I ask the group questions, I'm gonna slip in one of my first ones, a kind of a general one. In one of the earlier slides, where you showed the intersection of hazard and vulnerability and exposure, those three kind of factors, is it event specific as to which one has a greater effect than the other two? Or is there a general relationship where one is, is more than the others?
Depends on what type of event we're looking at. For example, when you're looking at drought and heat waves, that's basically hazard. So these are two different hazards that can have significant interactions with each other. Now, of course, vulnerability is always important. That defines sometimes severity of impact. So it all depends. So all of them are important. Again, the question is from what perspective you're looking at compound hazard. If your goal is to analyze the risk of occurrence, then you're only looking at hazard. But if your focus is on impact, then obviously you have to consider all of them at the same time. Exposure matters, vulnerability matters, and also frequency from hazard perspective. So it comes down to the question of what is the question that you're answering. When you're analyzing compound events with human drivers, then always vulnerability is a really, really important part. And there are many different types. Even for drought events, you can have significant human dimension. If you have a society in which the water demand is increasing over time, obviously, if the same drought that's happening now happens again 20 years from now, because your water demand is higher, your impact will be more extreme. So the same event means the same hazard, but your impact will be more significant because you need more water in the future. In that case, vulnerability is really, really critical. So again, it comes down to what is the question.
Yeah, so the impact, I mean, to society, of course, the impact, is what really matters, right? So the vulnerability and then the exposure to the hazard,
yes,
it becomes more important. One other quick question. So I think you already answered this. My question was like, to what extent, are the current federal responses to disasters consider, what your work is about, the compounding and cascading aspect of hazards, and also, well, let me just leave it at that first.
Did you say satellites?
Well, so I was wondering whether the current, federal agencies' responses to disasters, how much of the kind of things that you're working on, the compounding, cascading aspect of these disasters, do they consider in their program in responding to disasters?
Yes. This topic became really popular. Back in 2013, when we published our first article on this topic, obviously there was not a lot of papers, but now over the years, now there is a lot of interest. And Army Corps has formed a committee. I'm part of that, to develop guidelines specifically for coastal environments. So now federal agencies are moving toward guidelines. ASCE, American Association for Civil Engineers, is responsible for design guidelines, has exactly the same thing in progress. So they have a committee. I'm also part of that. We're designing design guidelines, basically, specifically for consultants and engineers to consider risk of multiple hazards when they are planning for seawalls, levees, and flood protection. So the interest is growing, and eventually it will happen.
Mm-hmm. Okay, great. So anybody Have questions?
Yeah, this is Brian, and actually, Amir, thanks for answering the question from Bill. Actually, because the question that Bill asked about how your research is incorporated into, well, you answered that you are serving on a committee that is trying to incorporate some of this research into guidelines. Actually, that was one of my questions too. And I was wondering, so this is maybe a follow-up question to that answer. The question is, and actually I have a total of 3 questions, but I'll just ask 2 of them first. The first question being on the standards and on the guidelines that you are trying to incorporate. Now, are those guidelines, to what extent are there metrics or to what extent are there metrics to encourage the adoption of these guidelines to reduce, say, the cost of infrastructure damage? I mean, the cost of infrastructure damage would be a potential metric that the government can track over time if those guidelines were adopted. So is there any thinking about what those metrics are that can be attached to the guidelines that you are developing? And then the second question after that, maybe the second question is maybe a little bit easier, but you had mentioned the difference between hydrological failure and physical failure, and I was wondering if you could explain a little bit more on that. I didn't quite catch your explanation about the difference.
Sure. So about the first question, when it comes to design guidelines, like official guidelines, there is no general metric. If there is, it's based on risk. If a kind of event has a high risk of occurrence above a certain acceptable level, then you need to account for that in your design. That's how it works. It's the same for earthquakes. It's the same for floods and other. So basically, if an event has a chance of significant damage, especially human life, then that's sufficient for agencies and regulators to come up with the guidelines to basically protect lives and significant damages. So there is no dollar value. Dollar value actually is irrelevant. Even if something turns out to be very expensive, but it is necessary to save lives, then still it will end up in your guidelines. So guidelines are not based on potential dollar value of damages. It's based on chance of causing loss of life, especially loss of life, and also significant damages or disruption in daily life. So basically, if agencies and regulators are convinced that a certain event can cause problems, even if there is no estimate of dollar value of damages, they have sufficient information to move forward with updating guidelines. The problem is updating guidelines takes a lot of time. There are many agencies involved. There are lots of legal issues involved. So part of it is science, but a lot of it is policy and legal issues. So it takes a long time. By the way, we have already, ASC has already published what they call it manual of practice. Manual of practice is like the first step. It explains the methods that are out there. It encourages, consultants and designers to use it. Even now, it's not mandatory. And usually they start with manual of practice, and then the next step is design guideline that we're working on right now. And once it is in design guideline, that everyone has to use it, even if it turns project more expensive and whatnot. So there is no metric. I hope I've answered your question. About the second one, so most of my talk was about hazard, like co-occurrence of different events. So that is basically part of reliability analysis from hazard perspective. That gives us hydrologic failure. Then if you want to really know if levee a particular levee in your city will fail or not, then you need to have a structural or geotechnical model where the forcings are different drivers, like a certain ocean water level, a certain amount of precipitation, and a certain amount of river flow, And we just published a paper that shows how to do this. And we focused on a levee system in Sacramento area. And in that case, you build a numerical model of that levee, then you force it with different ocean water levels and different precipitation levels, many different combinations of different hazards, and you look at the physical performance of that levee. If it fails, then you have physical failure. And in the paper we recently published, I haven't presented it here, we showed that, again, if we ignore the interactions between different drivers, we underestimate the physical failure probability too. Did I answer to your question?
Yeah, thanks. Actually, I have a comment about the regulatory part, and you raise a good point, because this feeds into one of the sessions that Bill and I are organizing in the upcoming ESUP winter meeting. So I will give a little bit comment about the cost part that you mentioned, that it's not relevant, but actually that's not quite true from the legal perspective, because I know about the legal perspective for regulations. But let's not get there first. I think we should come back to it, because I've got another question that relates to what your student is working on in terms of post hoc analysis of the effects of fire. But we have some other questions for you, so I wouldn't want to hog the time. Like Bill, I think Sun Ziheng, Jensen Soon has a question, so I'll come back to my questions later if we have time.
So do you want to just unmute and just ask the question?
Yeah. Sorry, I just came from the HU and I didn't realize I can speak directly. So it was fantastic. Can you elaborate a little bit on how the early mantling of the snowpack and the slower, you showed that in your figure, the SWU is becoming smaller when the temperature is rising. How does that change causes agricultural drought and impact the downstream societies?
Very good question. Actually, earlier this year, we published a paper in Nature Climate Change, and it focuses exactly on changing snow and impact on ag industry. So I can send you that paper. So we show that basically with rapid snow melt, you have high water episodes, but dry summers, and it will impact crop yield. And we have quantified it for different types of crops and in different parts of the world. So yes, it will have even more impact in the future.
So can you? So is there any difference? The impact on the mountain agriculture and the impact on the plain, like the downstream agriculture. Will that be some differences?
Yes, so actually we looked at downstream agriculture, because basically snow is happening in mountain area where you don't have ag right there, but basically we looked at downstream basins and what fraction of the ag water comes from snow, and we focused on basins where they rely on snow water equivalent, basically.
Great.
So we looked at how it propagates downstream.
Okay, sounds good. Looking forward to your paper. Thanks.
Sure.
Okay, a related question. So I was just wondering, you said the fires are increasing elevation, like going above the snow line. So is that just rising in temperature, or the moving up the elevation of vegetation regimes?
Did you say, sorry, I didn't get your question.
So why is the fires occurring at higher elevation than before? Is that just the increase in temperature or changing in the vegetation up the elevation?
Yes, so we actually looked into this issue of fire temperature relationship and also fire precipitation relationship. So temperature has definitely a big impact. So it's a huge driver, but also in at least in California, basically this human-caused fires are also on the rise because more people are in mountains now than 50 years ago, and accidents happen, or fires that are left there, or they put out the fire, but somehow that fire burns later. A big part of that, this has happened near Santa Barbara recently. So it's a combination of climatic drivers, climate change, climate warming, and also human activities, increased human activities.
Okay, thanks.
Hey, Bill, this is Dave Jones. Can I ask a question?
Oh, sure. Yes, Dave.
Hey, how are you? Just to say hello. Hi, Amir. Whoops, excuse me. Let me just fix something here. There we go. Hello. Amir, thanks for the presentation. I'm the co-chair of the ESIP Disaster Lifecycle Cluster. And I was just wondering if any of your research has been looked at by the National Weather Service to help them improve their communication of compound threats, and whether or not some sort of vulnerability index might be developed based on some of your work.
No, I haven't interacted with National Weather Service. I have interacted a lot with some NOAA colleagues, mainly on the drought and heat wave side, and I work very closely with Army Corps, and also BMO approached us. We are in contact with them, but National Weather Service not yet.
Okay, great, thanks. We're doing a little bit of work with the Weather Service in burn scar areas for the debris flow estimation, and USGS is putting together a product which is debris flow probabilities in burn scar areas. I was just wondering if I'll have to talk to a few people, see if they've heard about any of your research. Thank you.
Thank you. That would be great.
Anybody else with questions?
Yeah, Brian, I'll push on with my other questions. In fact, this actually relates to what Dave Jones was just talking about, because Dave, I remember that this was not long ago. You were demonstrating, and by the way, Amir, I'm going to try to tie together something that Dave Jones showed and something that you said at the end of your talk. Amir, you said at the end of your talk, this regards to post hoc fire analysis of events 1 or 2 years maybe after a fire that have an impact, but those tend to be kind of hard to study. And so my question in part regarding the work that your student is taking on has to do with sampling power and the fact that these are post hoc analysis, and yeah, you need to troll through reams of data, and some of them could be citizen science data or pictures that people took in order to gather enough data to do the post hoc analysis, and that tends to be challenging because of the uncertainties involved in that. And so wanted maybe your reflections on that. But how this relates to what Dave has showed previously. Dave Jones, I think, Dave, correct me if I'm wrong, but I think you were also interested in exploring with the NOAA folks the use of images taken after the fire in the field by, I don't know, by experts or by citizens or whatever. But I remember you were trying to show a tool to maybe it's even GeoCollaborate, to show how GeoCollaborate can be used to share these images. And so going back to Amir's students' research, I'm thinking maybe even some of these images can be part of that data for post hoc analysis, but I'm not entirely sure, and that's why I want to get maybe Amir's feedback and Dave Jones also about the uncertainties regarding the unavailability, or whether it's going to be hard to find enough data to do that kind of analysis. And so I'm going to throw it back to you guys.
Can I add a little bit to that question? So give you a little bit more context. One of the challenges that the National Weather Service has is to assess the quality of the soil during and after wildfire burns and then gets put out, because the hydrophobicity changes in the soil, and it changes the flash flood guidance and debris flow guidance for downstream communities. And so there's a need out there to understand the quality of the soil as soon as these fires are out and it's safe to go in there, or to image, or somehow, whether it's remote sensing or whether it's USDA bear teams, or the Forest Service bear teams that go in to assess the situation. So so it's pretty challenging. I mean, there's some colleagues using remote sensing data to try to understand what that is, but it seems like you need feet on the ground, taking pictures of soil, and then getting those pictures back in to the National Weather Service so they can assess the situation. And I think Brian was referring to GeoCollaborate, which is our technology to share data in real time across platforms, so we can really increase the awareness of the soil conditions and potential debris flows.
Yeah, these are all good points. In fact, I have a student, Charlotte Love. She had this idea of collecting data from citizens, and she even created an app called EarthTag, and we tried it, but there were lots of challenges and we couldn't secure funding for the app. It didn't go anywhere, but we even created an app to collect post-hazard data. But yeah, it is challenging. So right now we have an NSF rapid project. We go to burned areas right after wildfire, and we collect soil samples from burned and nearby unburned areas. And the goal is to kind of understand how soil characteristics change. But yeah, it is very challenging. It takes time, and with limited resources, we can only sample a fraction of fires this year.
Yeah, just a little bit of feedback there too. It's really, it's something that's I think of great interest to the Weather Service, but finding out who would actually collect that information in their course of their normal activities, whether or not the bear teams that go in, and that's the burned area emergency response assessment teams, whether they could do it and sort of, upload or text in pictures or things like that in their normal course of work, because getting people to kind of get into those burned areas is a tough thing, as you know, and so it's it might be a challenge that will be taken by the remote sensing community as more and more spectral analysis can be done, perhaps on soil quality, and how much is enough, what kind of information is good enough to help the Weather Service make their modifications to how much rain might be required to create those debris flows depending on the soil conditions.
Absolutely. And we have also a collaborator who takes samples to calculate shear strength of the soil, and that's very unique. It's never been done before. So we want to understand how shear strength changes, and that means how likely it is to eventually cause debris flow flooding. So that's work in progress, but hopefully next year we'll have some results on this topic.
Would you mind elaborating on some of those methods? I know you said it's new and you're going to publish, but. So
you mean the data that we're collecting?
You said you said it hadn't been done before on testing the soil. What's the steps for doing those methods? What
we are doing right now, we are collecting soil moisture, electric conductivity, salinity information, and also hydraulic conductivity and shear strength from burned and nearby unburned areas. We are in the process of data collection now. This year we had lots of fires in California, so we are going to different sites. As soon as we can get permission, we go in. We have already collected data from 5 wildfires, and there are at least 7 more that we are waiting for permission. And in addition to these local scale samples, we also fly drones, so we collect infrared images and also aerial images, just regular photos. In 2 locations, we were able to also fly hyperspectral, but our hyperspectral sensor is damaged. We are trying to replace it soon. And the idea is to, again, somehow synthesize all these data sets and find a way to quickly assess soil characteristics and likelihood of debris flow generation down the road.
Thank you for that clarification. Can I ask one more? Do we have time for that?
Sure.
Okay,
Yeah,
I was wondering, because you're collecting the data after the fire, are you going to be using any of like the Forest Service data about what it was like before the fire happened, or are you only using the post-fire? Because I know you said you're comparing where it was burned to where it wasn't burned, so does that help eliminate the need to get before and after samples?
Right, that's the idea. I mean, ideally you want to have before and after, but the problem is you never know where the fire will happen, and Forest Service data are very coarse. You should be lucky to end up with a place where there is before fire data and then wildfire. There are some locations where limited data is available immediately before fire, but not everywhere. So yes, the idea and unburned just to somehow eliminate the need for pre-fire data.
Yeah,
well, thank you. I appreciate that.
Up on, sorry. Oh, yeah, I'm just curious about the shear strength changes you mentioned post-fire. Is that due to changes at the soil granular level or in the kind of the chemical level?
Yes, so when basically soil burns, this cooking process changes soil characteristics. Soil may not absorb water for a while.
Right.
Strength of soil is related to moisture as well. So moisture is important, cohesion is important, lots of other properties. And our hypothesis is that soil shear strength changes because of this intense fires. But again, to what extent, I don't know yet. We are still collecting data.
Okay, yeah, I'll be interested to, yeah, well, once you have some, further results from the field and or in the lab, I'll be interested to,
For example, the hydrophobicity issue definitely changes moisture content of the soil.
Right.
That theoretically should change shear strength.
Mm-hmm. Okay, very good. Thank you. Any other questions? I have 402 right now.
Bill, Zhiheng has another question in the chat box.
Okay.
Yeah, I think it's just a follow-up question. So does the sample collection go to the root zone or it's just the surface?
No, it's just the surface.
Okay, thanks. Thank you.
Sure.
Hey, Bill and Brian, thanks so much for the invitation to join. I really enjoyed it. And Amir, thanks for the presentation. Appreciate it.
Yeah, thanks for coming. Yeah, really good to have you here. So if there's no additional questions, or I guess we can always contact me afterwards, because I have some more questions I want to ask, but in the interest of respect everybody's time. So Amir, thanks very much again for a really, really interesting talk. And I think there are areas of possible collaboration So definitely would like to follow up with you on seeing where some common areas between what you're doing and what our cluster is working on. So we'll keep in touch with you.
Thanks for the invitation. It was really a fun meeting. Thank you. Appreciate it.
Great. Yeah, thanks again. Thanks, everybody. Well, talk soon.
Thank you.
Bye.
Thanks. Bye-bye.
Bye-bye.